Okay, in this video I'm going to look at an example of finding eigenvalues and eigenvectors for a 2x2 matrix. So this certainly generalizes to any n by n matrix, but the arithmetic can get very tedious, especially if you're doing it by hand. But this is the basic process. So to solve for the eigenvalues, lambda sub I, and the corresponding eigenvectors, x sub I, of an n by n matrix A, we'll do the following. So the first thing we're going to do is we're going to multiply an n by n identity matrix by the scalar lambda. Step 2, subtract the identity matrix multiple that you found in step 1 from the matrix A. Step 3, we'll find the determinant of the matrix and the difference. So you'll basically just find the determinant of the matrix that you find in step 2. Then we'll solve for the values of lambda that satisfy the equation. We look at the determinant of A minus lambda times the identity matrix equals the 0 vector. So again, you're just basically, once you find the determinant, it says set it equal to 0 and solve. And then we're going to solve for the corresponding vector to each lambda. So let's do that here. So a few steps, but should be able to hopefully go through it relatively quickly. So just to write everything down. So we're going to find the eigenvalues and eigenvectors of the matrix A with entries 7, 3, 3, negative 1. Okay, so the first step, again, we'll just take lambda and multiply that by the identity matrix. So that's just going to be lambda. Again, the identity matrix for a 2x2 matrix will have entries 1, 0, 0, 1. So that just gives us lambda, 0, 0, and lambda. So again, you'll just have lambdas along the diagonal of your identity matrix. Well, it will no longer be an identity matrix, but you'll just have lambdas along the diagonal and zeros everywhere else after you multiply the identity matrix. So step 2, we'll take our matrix A and subtract lambda times I. So in this case, our matrix A again has entries 7, 3, 3, negative 1. And it says just subtract lambda, 0, 0, and lambda. And again, remember, you just subtract respective entries. So the top left entry will be 7 minus lambda. Then we would have 3 minus 0, which is just 3. We'll have 3 minus 0, which again will just give us a 3. And then we'll have negative 1 minus lambda. Okay, so those are our 4 entries. Now, step 3, the way we had it labeled a second ago, we're going to find the determinant of this matrix. So we're going to find the determinant of the matrix with entries 7 minus lambda, 3, 3, and negative 1 minus lambda. And recall to find the determinant of a 2x2 matrix, we take the top left entry, multiply it by the bottom right entry. So we'll have 7 minus lambda multiplied by negative 1 minus lambda. Then we use a minus sign. We take the bottom left entry, multiply that by the top right entry. So we'll have 3 multiplied by 3. Okay, so let's see if we can't simplify this. We'll have negative 7, looks like minus 7 times lambda. We'll have a positive lambda, and then negative lambda and negative lambda will be positive lambda squared. Then we'll have minus 9. So I'm going to write that as lambda squared. It looks like we're going to have a negative 6 lambda, and then negative 7 minus 9. That's going to give us just negative 16. Okay, so step 4, I think I can put it in here. We take that equation. So lambda squared minus 6 lambda minus 16. We set that equal to 0 and we solve for lambda. So no need to waste paper. So lambda squared minus 6 lambda minus 16, that's going to factor. That just factors as, I guess, lambda minus 8 multiplied by lambda plus 2. So we'll set that equal to 0. Well, if you set each factor equal to 0, we'll get the solutions of lambda equals 8. And by setting the second factor equal to 0, we'll get lambda equals negative 2. Okay, so now we've got our values for lambda. Those are going to be our eigenvalues. Okay, so these are the eigenvalues. And now we need to find the corresponding eigenvectors. Alrighty, so what we do now, step 5, we look at that matrix we formed, the A minus lambda I, so that was again the matrix that we found here. So I'm going to rewrite that. So we've got 7 minus lambda, 3, 3, and negative 1 minus lambda. And now we've got to do a few more computations. Okay, so the first thing I'm going to do is I'm going to start with my lambda value of positive 8. We substitute that in. So we'll get 7 minus 8. We still have a 3, a 3. Then we'll have negative 1 minus 8. And that's going to give us negative 1, 3, 3, and negative 9. So now what we do, I'm going to call, I think in my original notes maybe I called it A, but our original matrix was A, so let me maybe call this, I don't know, I'll call this the matrix B. Now what we do is we solve the equation. We'll take matrix B multiplied by the vector x equals 0. We have to solve this. So what we want to do is we want to solve, we've got negative 1 times 3 times 3 times negative 9. The matrix with the corresponds to the vector x here, we'll just write little x of 1 and x of 2. And then we've got our 0 vector here. So to solve this, I'm just going to use a little bit of row reduction. So we can write this as negative 1, 3, 3, negative 9. There's my zeros. I'm just going to do some row reduction. So to solve this, it looks like to me we could take 3 times row 1, add that to row 2 to give us our new row 2. So if we do that, the first row, nothing's going to change. We'll have negative 1, 3, and 0. So negative 1 times 3 plus 3 will give us 0. 3 times 3 will be 9, plus negative 9 will give us 0. And we still have a 0 at the bottom. So again, this is now going to correspond to x1 and x2. So that gives us our relationship. It says that negative x1 plus 3 times x2 equals 0. And we can simply add the x sub 1 over and write that as 3 times x sub 2 equals x sub 1. And now all you have to do is just pick some values. Okay, so the easiest ones to me, I'm going to let x sub 2 equal 1. And if we let x sub 2 equal 1, well then we'll have 3 times 1, which will give us our value for x sub 1. So it says if we let x sub 2 equal 1, it says x sub 1 is going to equal 3. That's going to be the eigenvector that corresponds to the eigenvalue of 8. So the eigenvector in this case will be the vector with entries 3 and 1. Okay, so that eigenvector again goes with the eigenvalue of 8. And you can check, if you want to, you can take the matrix that we started with, 7, 3, 3, negative 1. Let me write this down. You can check that if you take that starting matrix, 7, 3, 3, negative 1, if we multiply that by our eigenvector, again, which has entries 3 and 1, that'll be the same thing as when we take our eigenvalue, which is 8, and multiply that by the eigenvector of 3 and 1. You can check that on the left side, if you do this, we'll get 24 and 8 as the entries. And on the right, we'll get, 24 and 8, just like we should. So you can always check it. And again, right, 7 times 3 is going to be 21. 3 times 1 is 3. So 21 plus 3 will give us 24. 3 times 3 is 9, plus a negative 1. Well, that's 9 minus 1, which gives us 8 on the left. So, hey, in fact, that does work out. Okay, so halfway there. Now all we have to do, we're just going to do the same process, except now I'm going to use our lambda value of, what was it, I guess -2. And do the same thing. We're just going to do just like the exact same thing. So now if we let lambda equal -2, well, in this case, we're going to get, we'll have 7 minus -2. We've got an entry of 3. We've got -1 minus -2. And that's going to give us 9, 3, 3, and I guess we've got -1 plus 2, which will give us an entry of 1. And just like before, what we do is we have to solve that matrix equation. So I'm just going to skip writing down this step. I'm just going to go ahead and jump to the row reduction, right? So once we found our matrix, we just basically did row reduction to find the relationship. So I'm going to do the same thing. I'm going to do the row reduction. So we've got 9, 3, 3, and 1. So different ways to do it. To me, it looks like the most simple way is to take -3 times row 2 and add that to row 1 to get our new row 1. So if we do that, row 2 is not going to change. And again, you can check -3 times 3 plus 9 will give us 0. -3 times 1 plus 3 will give us 0. We'll still have a 0. Zeros at the top right. Again, this corresponds to x1 and x2. So now we can write our equation. We've got 3x of 1 plus x of 2 equals 0. Or equivalently, that x of 2 equals -3 times x of 1. So the same thing. You can just pick values. If we let x of 1 equal 1, well, in that case, we'll get x of 2 equals -3 times 1, or -3. So it says the eigenvector, the other eigenvector, will be the eigenvector 1 and -3. And again, that corresponds to the eigenvalue of -2. So that's all there is to it. So, obviously quite a few steps. When I say all there is to it, I don't mean to make it sound like there's nothing going on. There's definitely quite a few steps, but no one of them was terribly bad. Again, this is something you definitely don't want to be doing by hand. A 3x3 one, even finding the determinant of a 3x3 matrix can already be a little obnoxious. So once you get to anything beyond that, you certainly, and you're not going to be expected to do these by hand, a 4x4 matrix or a 5x5 matrix in class on a quiz or a test, unless the instructor is just a real masochist. So again, then you just you'll use some sort of some sort of software package, and it'll grind these out in a split second. But again, it's always good just to kind of know what's going on, what's happening, and so maybe I'll do a 3x3 matrix example if people really want to see it. Again, it's just going to be the same process, just long and drawn out. Again, the only thing that's going to be much different is just going to be finding that determinant. It's going to take more effort to do some row reduction. There'll be a little bit more work on these equations, but other than that, again, it'll be the same process. So, all right, I hope this makes some sense on how to find eigenvalues and eigenvectors.